Hey guys, Dr. Brown here with Kubo Math, and tonight we have the coolest of cool problems that we're going to work dealing with revolving an area around an axis to get a volume, but then we're going to drill a hole in it and remove a certain amount of the volume, the overall volume, and then calculate the diameter of that hole based on the volume that's been removed. So let's get after it. This is a good problem. Okay, I'm just going to actually do something a little bit different. I had worked this a few moments ago and it looked so well. Well, I don't know if it looks well, but I didn't want to erase it because this is really for a few guys here at TSU. And so I thought I would do the video, get it to them as quick as I can. Okay, I'll just read the problem. A solid is generated by revolving the region bound by y equals 1/2 x squared and y equal 2 about the y-axis. A hole centered along the axis of revolution is drilled through the solid so that 1/4 of the volume is removed. Find the diameter of the hole. Whoa, isn't that cool? Okay, that's more of a good machining problem that you might run across in your work as a mechanical engineer or civil engineer. Okay, I've drawn y equals 1/2 x squared. So if you set 1/2 x squared equal to 2, you'll find this point 2, -2. You'll find that that's the bounds of that curve and y equal 2. Now we're just going to think about what's in the first quadrant here, about how we're going to rotate that around the y-axis. So the way I set the problem up was, first I'm going to find the volume of the revolution of that region. Now notice it's not this region, but it's that region, because that's the region bound by y equal 2 and y equals 1/2 x squared. It's not that. Okay, so I'm going to find the overall volume first, and then I need to think about, well, I did a swag, scientific wild, you know what, guess as to what I thought the diameter would be close to. And then I need to think about the region, the volume associated with that curvature, that as I drill the hole, it's not included in the volume that gets removed. So we'll talk about that. First, let's do the shell method with a differential, a rectangle that represents dx. I set it up parallel to the y-axis. Okay. Now I know I've got the integral of p of x times h of x dx, and I'm integrating that from 0 to 2, and it's 2 pi times that. So what is p of x? It's the distance that my rectangle that I've drawn is from the axis of rotation that I'm rotating around. Well, that's x, okay? So that's p of x. What's h of x? Well, if it were this region, it'd just be y. But it's not. It's 2 minus y. So 2 minus 1/2 x squared. So I'll put that in here. So now I have my volume as 2 pi times the integral from 0 to 2 of x, which is p of x, times h of x, which is 2 minus 1/2 x squared dx. So we'll just multiply, distribute the x inside. 2 times x is 2x minus 1/2 x cubed dx. So now let's integrate. So this will be x squared over 2. So times that 2, those would cancel, minus 1/2 times x to the 4th over 4. And all of that's going to be from 0 to 2. Okay, now I have 2 pi times x squared minus x to the 4th over 8. Excuse me, 2 times 4 is 8 from 0 to 2. So now if I plug in the numbers, 2 squared is 4. X, or 2 to the 4th, 2 times 2 is 4, 2 times 2 is 4, 4 times 4 is 16, 16 over 8 is 2. So now I have 4 minus 2 is 2, times 2 pi gives me 4 pi. Now, so the volume total of that rotation around the y-axis is 4 pi. Now the problem said I'm going to drill a hole down through this region right here, down along the axis that I've rotated around, such that, what did it say here, is through the solid, so that 1/4 of the volume is removed. What is 1/4 times 4 pi? It's pi. So the volume of my hole that I'm drilling is pi. Okay. Now at that point, I had to think about, well, if I just drill a hole, so this cylinder represents the hole that I've drilled. I know the height is 2, so h is 2. Now you've learned pi r square h equals the volume of a cylinder. I would encourage you to learn that in terms of diameter. So d over 2, r equals d over 2, correct? So if I have d over 2 squared, I end up with d squared over 4. That makes more sense from an engineering perspective than pi r squared. The radius is not referenced. I mean, the center of a hole is not what they're going to talk about on the drawing. They're going to give you the diameter. Now they may show you the location of that hole, but it'll be listed in diameters, not a radius, typically. So pi d squared over 4 times h is the volume of that hole that I'm going to drill if it were a true cylinder. So if h is 2, I have pi d squared times 2 over 4 gives me pi d squared over 2. Now, it said that's the volume of the hole, but we know the volume of the hole is pi. So I can set this pi equals pi d squared over 2. So divide out the pi, I end up with, and then multiply by 2, I have 2 equals d squared. So d equals plus or minus square root of 2. Now I can't have a negative hole size, so the negative, that doesn't make sense. So d is the square root of 2, which is approximately 1.41. Now that's my swag, because if I look at this hole, or the shape, you know, there's curvature at the bottom. So the volume here is not included in the volume of the hole. It's not there. So I need to subtract that volume from this estimate right here. I need to cut those corners off, if you will, and figure that out. Well, so I've drawn this a little bit larger now. So this represents this curve right here, and this represents the side of the hole. Now there's another one over here, obviously, which would be the diameter. So that makes this as diameter divided by 2. So now I'm trying to understand that volume right here and subtract it away from the total volume of my cylinder. Okay, so I set up a shell method, drew my differential. That's my vertical axis, and I'm rotating around that. And now, since I'm underneath this thing, y equals 1/2 x squared, so the height of this thing is 1/2 x squared, so that equals h of x. The distance that a rectangle is from my axis of rotation is x. So p of x is x, h of x is 1/2 x squared. So the volume of the hole is pi d squared over 2, which is the cylinder total that we calculated down here, minus my swag, forget the swag, pi d squared over 2 minus this integral from the volume that we're going to understand here, 2 pi times the integral from 0, and there should be a x, oh, never mind, 2 pi times the integral from 0 to d over 2 of 1/2 x squared times x, which is 1/2 x cubed. Okay, now I can multiply, take the 1/2 outside, 2 times 1/2, that cancels, it's 1, so pi times the integral from 0 to d over 2 of x cubed dx. So that gives me x to the 4th over 4 times pi from 0 to d over 2. And keep in mind, I'm still subtracting this volume from the volume of the total cylinder. Okay. Then if I keep going here, bring down the pi d squared over 2 minus pi over 4, just brought that 4 to the outside. D over 2 to the 4th power gives me d to the 4th over 16. 16 times, and minus 0, if I get the rest of that work done out here, 0 to the 4th is 0. Now 16 times 4 is 64. I need to get a common denominator. 2 will go into 64 32 times. I multiply this by 32 over 32. 32 times 2 is 64. So I have 32 pi d squared minus pi d to the 4th over 64. That's the volume of the hole. So let's go up here. So I multiply through by 64. Oh, I guess I erased a step there. Let me see if I can put it down here. Volume of the hole, remember, was pi. So if I factor out, I'm going to do this up top. So pi equals, I'm going to factor the pi out, so pi times 32d squared minus d to the 4th. Can you see that? Yeah, okay. So if I divide both sides by pi, it becomes, and that, oh, that's over 64. That's 1. Okay, pi divided by pi is 1. 1 times 64 is 64, which brings us to this point right here, okay? So I just moved to 64, subtracted it from the other side. So 0 equals d squared times the parentheses of 32 minus the diameter squared, close parentheses, minus 64. Now, I put in my swag number. Remember my swag for I thought the diameter, if it was a total cylinder, was 1.412. Okay, I ended up with an error of minus 4.17. Okay, I needed to increase the diameter, which we thought we would have to because that volume was not included in the overall cylinder. I jumped it up to 1.45. It was a minus 1.14. Up to 1.46. Oh, we're getting close. 1.47. It was too high, too large of a hole. 1.464 gave me a minus 0.008. For me, that was good enough. Okay. So the diameter of that hole is 1.464. That's a cool problem right there. So we ended up getting the total volume, took 1/4 of that, which told me what the volume of the hole was, and then we formulated what the volume calculations would be for the hole as a cylinder minus the volume associated with that curvature of y equals 1/2 x squared. Hey, why are we doing this? Sometimes maybe we think we're crazy. Together we're trying to build a better tomorrow and do that through math. We're trying to make you better engineers, guys. Keep studying. And that's all for now. We'll talk to you next time. Thanks.